Welcome, students. In this video, we are going to study limits at infinity. We are going to start with informal definition of limits at infinity. Then we are going to take a look at several examples of specific functions and their behavior at infinity. If the values of f of x eventually get as close as we like to number L, as x increases without bound, then we write limit as x approaches to plus infinity of f of x is equal to L. Similarly, if values of f of x eventually get as close as we like to number L, as x decreases without bound, then we write limit as x goes to minus infinity of f of x is equal to L. All right, here are several examples. So in first graph here, we see a plot of 1 over x. And if we take limit as x goes to minus infinity of 1 over x, we see that. So basically, if we scroll the values of x to the left, so if we scroll values of x alongside of x-axis towards minus infinity, values of y here are going to get closer and closer to y is equal to 0. So that limit is equal to 0. Similarly, if we scroll values of x towards the right side of x-axis, we increase values of x without bounds, and values of y get closer and closer to 0. So that limit is equal to 0. Basically, we have a horizontal asymptote at y is equal to 0. Here are several other examples of horizontal asymptote. So in first plot here, we have horizontal asymptote at L, y is equal to L. So as x increases without bound, the values of f of x get closer and closer to L. So that limit is equal to L. And as x decreases without bound, values of f of x get closer and closer to y is equal to L. So we have horizontal asymptote at y is equal to L. So y is getting closer and closer to L, but it will not touch that horizontal asymptote. All right, so here are several of other examples. Limit as x goes to plus infinity of inverse tan of x is equal to pi over 2. So we have horizontal asymptote at pi over 2, and other horizontal asymptote is at minus pi over 2. As we decrease values of x without bound, value of inverse tan of x gets closer and closer to y is equal to minus pi over 2. Here we have plot of 1 plus 1 over x to the power of x. And as we decrease values of x without bound, we are approaching this horizontal asymptote at y is equal to e. So this limit here as x approaches to minus infinity is equal to e. And similarly, as x goes to plus infinity, we also have the same horizontal asymptote at y is equal to e. So that limit is equal to e. We are going to prove that statement a bit later on. For now, you can confirm that, take that fact as granted. All right, now several other properties. Let's assume that limit as x is increasing without bound of f of x here exists. Then the following four properties are going to hold true. So we can move power across the limit sign. So limit of f of x to the power of n is equal to n's power of limit of f of x. And similarly will hold true when value of x decreases without bound. We can also move a constant. Let's assume that k is a constant, then we can move it out of limit sign. And same will also hold true as values of x decrease without bound. Since k is invariant of x, as we decrease or increase values of x without bound, that limit is simply going to be equal to k. All right, next definition is for infinite limits at infinity. If values of f of x increase without bound as x increases or decreases without bound, then we write limit as x goes to plus infinity of f of x equal to plus infinity. And similar definition for case when values of f of x decrease without bound. Now let's take a look at several examples of nth power of x, of limit of nth power of x. When values of x increase without bound, x to the power of n, that limit is equal to plus infinity for any positive values of n. And as values of x decrease without bound, that limit of x to the power of n is equal to minus infinity in case when n is odd, and equal to plus infinity when n is even. Oh, guys, I forgot to mention that coming back to this property here, we should mention that n should be positive. Right, so again, if limit of f of x exists, then we can move this power out of limit sign, as long as n is a positive. All right, so here are several examples of nth power of x. When y is equal to x, if we increase the values of x without bound, then the limit is equal to plus infinity. If we decrease values of x without bound, then that limit is minus infinity. For a parabola, we can see that in both cases, when we increase values of x or decrease values of x without bound, then limit of x squared is going to be equal to plus infinity. And a couple of other examples. So here, example for y is equal to x cubed and y is equal to x to the power of 4. All right, so we have the following nice property here. The end behavior of polynomial matches the end behavior of its highest degree term. So this limit as x increases or decreases without bound of a polynomial is equal to the limit of its highest degree term. To see why this is true, let's take a look at this limit here. Let's factor out x to the power of n out of brackets. So we will end up with c0 over x to the power of n plus c1 over x to the power of n minus 1, and so on. So the only free term is going to be cn. As we increase values of x without bound, we can see that these terms are going to vanish, and we'll end up with cn here. So limit as x goes to plus infinity, x to the power of n, cn. So when you have a polynomial, you should ignore all other terms and look only at a highest degree term. All right, let's take a look at the following rational function here. Let's try to solve that limit. We can not use limit laws for the ratio of two functions right away here, since a function in numerator doesn't have a limit as x goes to minus infinity, and same for function denominator. So we cannot express this limit of ratio of two functions as ratio of two limits. However, we can apply the following simple trick. We can divide both numerator and denominator by highest term in denominator. We'll end up with 4 over x minus 1 over x squared. In the denominator, we have 2 minus 5 over x cubed. So we divided both numerator and denominator by x cubed. Now let's see whether we can use limit laws here. Now limit of function in numerator is equal to 0, and limit of function in denominator as x goes to minus infinity is equal to -2. So both limits are finite and exist. So we can express this limit of ratio as ratio of limits. So we'll end up with limit as x goes to minus infinity of 4 over x minus 1 over x squared divided by limit as x goes to minus infinity of 2 minus 5 over x cubed. All right, as x goes to minus infinity, we have 0 in numerator. As x goes to minus infinity, this is 2. So the answer is 2. So here we could have used the following nice property: the end behavior of a rational function matches the end behavior of the quotient of the highest degree term in the numerator divided by the highest degree term in the denominator. So here we have a ratio of two polynomials. We can express that as limit as x goes to minus infinity. We are ignoring all other terms and we're looking at the highest degree term in numerator, which is 4x squared, and ignore all other terms in denominator except for the highest degree term, which is 2x cubed. So we have 2 over x as x goes to minus infinity is simply 0. Okay, let's take a look at the following problem. So limit as x goes to minus infinity of this ratio here. We cannot again use limit laws right away, since limit of function in numerator doesn't exist and limit of function in denominator also doesn't exist as x goes to minus infinity. Now we are going to apply a similar trick. We'll divide. However, this time we are going to divide by absolute value of x, both numerator and denominator. So we'll end up with the following fraction, with the following ratio. Now, the reason we are dividing by absolute value of x instead of x is that we want to bring this term here inside of square root operator. So we are going to end up with limit as x goes to minus infinity. So we have here root of x squared plus 2 over x squared. Here we have 3x minus 6. Now, as x goes to minus infinity, absolute value sign here will open with the minus sign, which leads us to limit as x goes to minus infinity, root of 1 plus 2 over x squared divided by minus 3 plus 6 over x. Now here we can use limit laws, since a limit of function in numerator exists and limit of function in denominator also exists as x decreases without bounds. So we'll end up with limit as x goes to minus infinity of root of 1 plus 2 over x squared divided by limit as x goes to minus infinity of minus 3 plus 6 over x. Okay, so z goes to 0, z goes to 0, as x goes to minus infinity. So we end up with 1 over minus 3. So minus 1 over 3 is the answer. All right. So again, guys, the reason we are dividing by absolute value is that we want to bring this term here inside of the square root brackets. You don't have to divide this by absolute value if x is approaching to minus infinity. If x goes to plus infinity, you can simply divide everything by x. All right, now let's take a look at limits of exponential function. So here we have a plot of y to the e to the power of x We know that ln of x is an inverse of that function. Let's remind ourselves to find if we have a plot of our function and we want to find the plot of its inverse, we have to draw a line y is equal to x, dashed line here, and we have to take a mirror image or reflection of it around that line. And so e to the power of x is an inverse of ln of x. We can reflect ln of x to find e to the power of x, and we can find the ln of x by reflecting e to the power of x about the line y is equal to x. So as x decreases without bound, e to the power of x, here we can see is approaching to 0. We have horizontal asymptote at 0, so that limit here is equal to 0. As x is increasing without bound, we can see the values of e to the power of x also increase without bound. So this limit here is equal to plus infinity. Now let's take a look at ln of x. As x goes to plus infinity, ln of x also increases without bound. So this limit here is equal to plus infinity. And as we can see here, we see that ln of x has vertical asymptote at x is equal to 0. So limit as x goes to 0 plus of ln of x is equal to minus infinity. The values of ln of x decrease without bound. Okay, so here we see a reflection about y-axis of e to the power of x. So let's recall that if we have function f of x and we want to find the plot of f of minus x, we need to reflect it about y-axis as we did here. And limit, as we can see, limit as x goes to plus infinity of e to the power of minus x is equal to 0. We have horizontal asymptote at y is equal to 0. And as x goes to minus infinity, values of e to the power of minus x, they increase without bound. So that limit here is equal to plus infinity. And finally, trigonometric functions. And here we see a plot of sine of x. The values of sine of x, they oscillate between -1 and 1, meaning that a limit as x goes to plus or minus infinity doesn't exist. Same will hold true for cosine of x, for tangent of x, and cotangent of x. All right, guys, that concludes our lecture on section 1.3 on limits at infinity. And in the next video, we're going to solve a bunch of problems using the properties that we learned today. Thanks for watching.